Okay, so good morning again, everybody. Here's the good old definition of the limit of a sequence. Let me also remind you, add to this, so let's mark this with a bullet, and add to this the next definition that we encountered, the limit being infinite. So that we say that the limit of an as n goes to infinity is infinity if, who remembers?
Oh, I have it here.
Oh, you have it there, right? I have it here, you know. For every, not for every epsilon, for every m, there exists an n such that if we go beyond the threshold index, then the elements of the sequence exceed m. Okay? So this is converging to a finite limit, L, and this is converging or diverging. Terminology is not consistent, but going to infinity. Okay? What we want to do today is take a step up from the little theorems concerning these two phenomena and study sequences, study some theorems that are a bit more sophisticated and will be very useful for the things we need sequences for. Okay, so for that, I want to remind you first the notion of monotone, monotonicity, but for sequences. So, definition, it's going to be very similar to the notion that we've encountered for functions, and it's going to make sense, of course. So, a sequence, an is let's say monotone, and now there are several possibilities, as you recall. Increasing, monotone increasing, if an plus 1 is greater than or equal to an. Does that make sense?
Yeah.
Okay. And there are two possibilities here to write in the definition. One is to write for every n. This means that from the very first element, every element is greater than or equal to the previous one. Or you can write from every n greater than some fixed n, meaning that you don't, you're not too strict on what's going on at the beginning, but you want it to be increasing from a certain point onwards. Okay? So maybe I'll write it like this: for every n slash for every n greater than n. Both definitions are okay. When you work with them, you have to make clear which one you're requiring or which one you're using. Okay? So maybe we will say that it's increasing if this happens, and it's increasing from a certain point if this happens. Okay? And then there are, of course, all the others. So we had strictly increasing if an plus 1 is strictly greater than an, and decreasing if an plus 1 is less than or equal to an, and strictly decreasing if an plus 1 is strictly less than an. And we even mentioned that there's a bit different terminology often used, calling strictly increasing, calling it increasing, and calling this non-decreasing. Same thing, just different terminology. So that's the concept of being a monotone sequence. Let's do some examples. So for example, so here's the first example, the sequence an equals 1 over n. What would this sequence be? Right, it's strictly decreasing. Does everybody agree? Strictly. And is this for every n or just from a certain n onwards? For every n, right. So this is strictly decreasing for every n. Note that the concept of being decreasing is not a limit concept. Okay, it's not something that we require ad infinity in any sense. It's a finite concept. We want it to hold for at every n, at every place you look. You look at two elements, you want the one with the bigger index to be smaller if it's decreasing. Okay? Yes?
And to prove that that's strictly decreasing, you can just plug in.
Well, how would you prove something like this? Well, plugging in is not a proof. Plugging in is, right, you can do induction, that's one option. Or, I think here it's even more elementary. What do you want to show? You want to show that 1 over n is greater than 1 over n plus 1. That's trivial, right? The denominator is bigger, the fraction is smaller. Do you agree? So here the proof, you don't need induction. Many times induction would be a tool, but here it's...
In general, not specific.
Right. In general, induction is a good tool. In this case, it's just completely straightforward. Okay? Good? Here's another example. Example 2. an equals -1 to the n times 1 over n. Remember the names for these? We had names for these. This was called harmonic sequence. And what did we call this? Right, the alternating harmonic. What about this one?
Nothing?
Well, it's not nothing. It's a sequence, but it's not monotone. That's what you meant, right? I know. So this is not monotone. Okay, so these four terms do not cover all the possibilities. They're sequences that are monotone are very special. And in general, a sequence needs not be monotone at all, right? So this one bounces back and forth. It's not monotone in any direction. Do you agree? Okay. What about an equals n squared over 2 to the n? Okay, so this one is not obvious just from a glance, right? So how do we get intuition? What do we do?
The order of the denominator is bigger than the order of the numerator.
Okay, so you claim that the denominator wins, right? As n gets bigger, 2 to the n beats n squared. Okay, so then what do you claim? That it's decreasing. How do you tackle an example if you don't have good intuition? What do? You start looking at the elements, right? Let's start looking at the elements. What's the first element of this sequence? You plug in 1, right? That's the first element. So a1 is 1 squared over 2 to the power 1. a1 is 1/2. Does everybody agree? Yes? What's the second element? You plug in 2. 2 squared over 2 squared. What's that? 1. Do you agree that the second element is 1? Okay. What's the third element? 3. 3 squared over 2 to the power 3. 9 over 8. So who claimed here that this sequence was decreasing? Oops. This looks kind of increasing to me. No, don't point at your buddy. I know it was you. Do you agree that this is an increasing sequence?
But how do we know later on it's not going to start?
Very good. How do we know that later on it's not going to start decreasing? Right? So in fact, that's what happens here. Okay, so if later on is now. Okay, so this one just starts in a deceiving way. What's the next element when n equals 4? It's 4 squared, that's 16, over 2 to the power 4, that's 16 too. So it's 1 again, right? And in fact, now it starts decreasing. So 5 squared is 25 over 32. and dot, dot, dot. You can do more elements and see that, in fact, the phenomenon here is that at the very beginning, it kind of tricks you. It seems like it's decreasing. Let me symbolically denote it like this. Oh, right. Confused myself, right? Right. It seems like it's increasing, but in fact, afterwards, it starts decreasing, and that continues on and on. Okay? So, this is, right, we didn't prove it. This is not a proof of anything. This is just a proof that plugging in the first elements can even get you the wrong answer. Okay, so this one, you do the first, if you do the first 20, okay, the first 3 you see that something went wrong, but afterwards you see the general direction. But maybe the first 1700 go in one way and then it changes direction. How would you know? Okay, so I want to prove this. I want to prove that this sequence, so the claim is that this is decreasing, and in fact strictly decreasing, for n greater than or equal to 3. That's what we claim, right? If we want to make this claim, we need to prove it. Okay? How do we prove something like this? What do we need to show?
The definition?
Right, the definition. What's the definition? So, proof of the fact that the third example is decreasing for n is greater than or equal to 3. We need to show that a n plus 1 is less than a n for every n greater than or equal to 3. That's what we need to show. Do you agree? Okay, so how do we show something like this? So a standard way of showing it is taking the quotient an plus 1 divided by an. If we show that this quotient is less than 1, that would imply this, right? This is if and only if the quotient is less than 1. Do you agree? As long as the an's are not 0, and in this case they're not because it's a positive sequence. Do you agree? So if we show that this quotient is less than 1, we're done. Right? Okay, so let's write what this is. So what's an plus 1? I'm looking at the formula for the sequence elements. So it's n plus 1 squared divided by 2 to the power n plus 1. That's an plus 1, right? Instead of dividing it by an, just so I don't write in Chinese, I can multiply it by the reciprocal. Do you all know that? Okay, so I'm going to multiply it by an, 1 over an, so it's 2 to the n divided by n squared. Do you agree that this is the quotient of an plus 1 over an? Okay, now things cancel out nicely here. Let's do that in blue. So the 2 to the n with the 2 to the n plus 1, there's only a single 2 is going to be left in the denominator. So let me denote that by canceling the n plus 1 with this. Do you agree? So what do we get? We get 1/2, and then we get n plus 1 divided by n squared. Do you agree to this? Okay. And let's rewrite that just one more time. So that's 1/2, 1 plus 1 over n squared. Okay? And what do we want? We want to show that this is less than 1. So this is what we want. Is this true? Right? If we show this, we're done. Right? So is this less than 1? So, well, it's not going to be true for any n. right? We know that. We know that it's only going to be true for n greater than or equal to 3, right? So let's start working on this. So this is less than 1 if and only if. So let's call this star. Star holds if and only if. This is short notation for if and only if. If and only if, let me multiply this by 2. So 1 plus 1 over n squared is strictly less than 2. And this is if and only if 1 plus 1 over n. Well, in fact, I think you can see it here. So let me write it a bit differently. I think it would be more convincing. Does everybody agree to this? Okay. So, and indeed, if n is greater than or equal to 3, then if n is greater than or equal to 3, then 1 plus 1 over n, well, let me write it. Then 1 over n, if n is greater than or equal to 3, 1 over n is less than 1 over 3. Do you agree to that? Less than or equal. If n is greater than 3, 1 over n is less than 1 over 3. Do you agree?
Yeah.
Then 1 plus 1 over n is less than 1 plus 1 over 3. Do you agree? Then 1 plus 1 over n squared is less than 1 plus 1 over 3 squared. Do you agree to that? And this I can calculate. So 1 plus 1 over 3 is 4 over 3, right? 4 over 3 squared is 16 over 9. And 16 over 9 is less than 2. Right? So if n is greater than 3, then 1 plus 1 over n squared is less than 2, and that's what we wanted to show. This implies this, and this implies an plus 1 over an is less than 1, which is the same as an plus 1 is less than an.
Can you please run over that again?
I can run over it again. Yeah, okay, so if you would find something like this in a book, it would start as follows. Suppose n is greater than or equal to 3. Then this holds. Then this holds. And then this holds. Okay? The way I did it is trying to let it lead me. Not as if I know what to write, but trying to decipher it and see where I head and what's going to happen. Okay? So I actually tried solving it and not just writing the solution. Okay? So I started by saying this is what I need to show. And then I said, okay, this is the same as saying that the quotient is less than 1. Okay? I plugged in the formula for the sequence, did some cancellations and stuff, and got to this claim, which is what I want to show. Okay? And then I argued that indeed, if n is greater than or equal to 3, this holds. Good? Everybody? So this proves that the sequence n squared over 2 to the n is indeed decreasing for n greater than or equal to 3, starting from the third element. Okay. Let me give you one more example. Well, I want to give two more examples. One of them I want you to try on your own. So, example number 4. Let's look at the sequence an equals n factorial divided by n to the n. You know what? Let's do this. Let's do this one as well. Okay? So, here intuition is even more tricky. Who wins? Who's of a bigger order, as you said? N factorial or n to the n? N to the n seems bigger, right? So the intuition is that this is increasing as well, decreasing as well, right? So let's do the same thing we did there. an plus 1 divided by an. And let's show that this is less than 1. Okay? So what is it? It's n plus 1 factorial divided by n plus 1 to the power n plus 1. That's an plus 1. Instead of dividing by an, I'm going to multiply by the reciprocal. So I have n to the n divided by n factorial. That's the reciprocal of an. Canceling out stuff, what can I cancel out? So n plus 1 factorial and n factorial, I can cancel the n factorial with the factorial. Do you agree? Does everybody agree to that? Everybody? Good. And now I have a single n plus 1 here. I can cancel that, this n plus 1, with the plus 1 here, with one appearance of n plus 1, which appears n plus 1 times in the denominator. Do you agree? Okay, so what's left, so what I have left here now is n divided by n plus 1, all of this to the power n. Do you agree? And n divided by n plus 1, for any n, this is a number which is less than 1, right? I'm dividing a number by something bigger. So this is less than 1. When I raise it to any power, it's still going to be less than 1. Do you agree? So this is less than 1, and this is in fact true for any n. So we showed that an plus 1 over an is less than 1 for any n, and this implies that an plus 1 is less than an for any n. Therefore, the sequence is strictly decreasing for any n. Okay, so this was kind of very similar to the previous examples. Sometimes the tools you need are induction, like somebody suggested. Sometimes just doing things like this. Sometimes it's even more straightforward, various cases. And the last example that I want to give is this example. An equals 1 plus 1 over n to the power n. So this is a very important example. Okay, we mentioned it. Do you remember why we mentioned this example? Right, this is a sequence that converges to E. Okay, we'll say that in a couple of minutes. But what I want to emphasize now is that this is an increasing sequence. Excuse me? I can't hear you. You have to raise your voice.
Isn't this sequence strictly increasing?
It is strictly increasing, yes. And when I write increasing, it includes the situation of strictly increasing. But you're right, this one is even strictly increasing. And proving this is not trivial. Okay, it doesn't follow from standard tools like this. You have to do something different. There are several different proofs. We're not going to spend time on them. They're at least the ones I can recall now are a bit long. We're not going to do them in class, but this is an increasing sequence. Okay?
Is it like enough in general to just say it's increasing, or do we need like a certain proof or a certain condition that will?
If you want to show that it's increasing, you need to show, well, you need to prove it.
I mean, for example, for this example, it's quite obvious because you have 1 plus some number which will always be greater than 1, and you have a power which is greater than.
But these n's change, okay? And we've seen that things can be tricky. No.
It says that it's increasing.
I don't think this is obvious. To me, it's not obvious, because I agree that the number you're adding to 1 becomes smaller and smaller, but the power you're raising it to becomes bigger and bigger. Okay? And these things can be extremely delicate and extremely deceiving. Okay? For me, the fact that this is increasing is not obvious. I mean, you can start plugging in numbers and maybe getting convinced, but it's not an obvious statement. You need to prove it. And it turns out that if you want to prove this by elementary tools like this or standard induction, it doesn't work, for free. You need to do more tricky stuff. Okay? Yes?
Can't you just make it the same denominator, so it's n plus 1 over n, and n plus
No. This is what you want to prove. You want to prove the definition. You want to prove that if you put an n plus 1 here and here, that's the n plus 1 element, that you get something which is less than or greater than if you put just n. You can't mix them. Okay? Here's my suggestion. Try. Don't be afraid to get your hands a bit dirty. Okay? Try. Take a piece of paper and try working this. See where the difficulties show up. See why it's not trivial. Maybe you'll find the proof that's not too hard. Okay? You got to try it. Don't try to run it through in your head. Later. I want to move on. Okay? So, this is the last example of monotone sequences that I want to give. And now comes a very important theorem. I'm not... let me emphasize something. Sometimes I don't understand your question or your idea. That can happen, that you're trying to convey something and maybe I'm not getting what you're saying. But we can't afford to pause on every remark and clarify it on the spot. Okay? I do want to, of course, answer every single question, but we're going to have to postpone some of them to the break or to office hours. Okay? So don't leave anything unanswered. That's not the right thing to do. Okay. So here comes a very important theorem, very useful, and it says the following. Every monotone and bounded sequence, every monotone and bounded sequence converges. Okay? Let me try proving this without saying a single word, but you're going to have to look at me. Okay? Look at me. Look at me. Look. Is that convincing?
Yeah.
Let me do it again. How many people got it? Raise your hand if you think you got the idea. Very good. Okay. So what I was trying the idea I was trying to convey without words is, okay, it's monotone, suppose monotone increasing. So here are the elements. They get bigger and bigger, but it's bounded. They can't just get bigger and bigger. It's bounded. So they do this. They don't have much of a choice. They're going to converge. And moreover, what are they going to converge to? What's this? The supremum. Very good, very good. And in fact, that's the proof. Okay? So the proof is, assume, so there are two cases here. It can either be monotone increasing or monotone decreasing. We're going to handle one of them and say that the other one is very similar. Okay, we don't have to write the argument twice, because it's just the same argument. So the way of saying that we're going to run the argument and then leave it to the reader to run the other case, is using these letters, W, L, O, G, which stand for without loss of generality. Okay? So we're not compromising the generality of we're not saying only monotone increasing sequences satisfy the theorem, but we're saying we're going to run this without loss of generality, assume that AN is increasing. If you want to do it for decreasing, run the exact same argument, but replace the trivial things that you need to replace. So supremum is going to be replaced by infimum, and greater than is going to be replaced by less than, and everything is going to be the same. Okay, so is it clear what these letters stand for and what I mean? Okay, now never use this without thinking. So it's only legitimate to use this when the proof or the statement you're trying to make really breaks into cases which are all equivalent, and that you don't need to, and to spell out each and every one of them would be just to repeat yourself. Okay? In some proofs, you need to break it into cases, and each case is very, very different than the other one, and then you need to prove it for all the cases. Okay? Here, they're very similar. So assume, without loss of generality, that AN is increasing. By the axiom of choice, by the axiom of completeness, right? That's what we called it. Axiom of choice is something completely different. By the axiom of completeness, AN has a supremum. Right? Why? What was that axiom?
And every set of numbers, that's a maximum of real numbers.
Every bounded set. And we know that it's bounded. Every bounded set of numbers has a supremum. That was the axiom of completeness. No, that's given here. Okay, it's given that the sequence is bounded. Monotone and bounded. I'm assuming not that it's just any monotone. I'm taking one of the cases in which it's increasing. But the assumptions are still hold. So by the axiom of completeness, AN has a supremum. Let me emphasize it, since it is bounded. Okay? So let's denote the supremum. Denote L equals the supremum of AN. Okay? And usually we denoted the supremum by different letters, like S or maybe M. This is kind of suggestive, the fact that I'm denoting it by L, because what do I want to show? That this is in fact the limit. Okay? We claim that the limit of AN equals L. Can you hear all those cats outside? Wow. I wonder what's the special occasion today. Okay, so this is our claim that this supremum is in fact the limit. Okay. So in order to show that, we are going to need to resort to the definition of the limit, but it's going to be very basic, very, very basic. So let me remind you, let's take a quick glance at this board. The limit is L if, for any epsilon, from a certain point onwards, all the elements are in an epsilon neighborhood of L. Remember that this is the same as saying AN is between L plus epsilon and L minus epsilon. Do you agree?
Yes.
So we need to show that for any epsilon, from a certain index onwards, all the elements are between L minus epsilon and L plus epsilon. And L is now the supremum. We took the supremum of the sequence. Okay. Let's do it. Very easy in this case. Let epsilon be greater than 0. L minus epsilon is not an upper bound. For an. Why? Because by definition of the supremum is the least upper bound, the smallest upper bound. So if we take something smaller than the supremum, it can no longer be an upper bound. Do you agree? Because if this were an upper bound, this would be a candidate for the supremum rather than L itself, because it's smaller than L. Do you agree? So it's not an upper bound because L is the supremum. Does everybody agree to this? Okay. Therefore, there exists an element, let's call it An with a capital N. There exists an element such that An, sorry, we called it capital N, An is greater than L minus epsilon. Because if all the elements were less than L minus epsilon, then L minus epsilon would be an upper bound, and we agreed that that's not the case. So there must be an element greater than L minus epsilon. Do you agree? Everybody? Okay. Since An is increasing, since the sequence is increasing, for any n greater than n, we have An, this element that we knew was bigger than L minus epsilon. And since it's increasing, if we take an n greater than n, then A small n is going to be greater than A capital N. That's the definition of increasing. Do you agree? But L itself was an upper bound. So all the elements, for any n, these are less than or equal to L. Nobody can exceed L, because L is an upper bound. And this is, of course, less than L plus epsilon. Done. End of proof. Let's go over it one more time. We took L to be the supremum. We said all the elements are going to monotonely get closer and closer, but they cannot exceed L. That's the idea. Formalizing it, take L to be the supremum. It exists because of the axiom of completeness. Any bounded set has a supremum. We assume the sequence is monotone increasing, and you can see that handling the other cases completely analogous. And then we said the following. Take epsilon. L minus epsilon is not an upper bound because L is the smallest upper bound and this is smaller. Therefore, there must be an element that's bigger than this because it's not an upper bound. It cannot be that all of them are smaller than this. The sequence is increasing. Okay, so maybe I'll write, instead of exists An, let me write exists N. There exists an n such that An is greater than this. And let me marker this. Since the sequence is increasing, for any n greater than n, we have An was bigger than L minus epsilon. If little n is bigger than An, monotonicity implies this. And all the elements are less than L, because L is an upper bound, which is in turn less than L plus epsilon. So we have L minus epsilon is less than An is less than L plus epsilon. So there in blue, you have the definition of the limit highlighted, and we just proved it. Clear? How many people followed the proof? Good, good. Questions? Yes?
What's the axiom of completeness?
That's just a statement that we remarked when we discussed supremums and infimums, that every bounded set has a supremum and an infimum.
If it's bounded, does it converge?
A set, the notion of convergence, we didn't even mention those words when we talked about just sets of numbers. You have a set of numbers, an interval. The interval between 1 and 5. What does it mean that it converges? But it has a supremum and an infimum. Okay, so this notion of supremum and infimum in upper bounds and lower bounds is not a limit notion. That's what I said about the sequences as well. Okay, the limit notion is relevant to sequences, okay, or to functions, which we discussed previously. Okay, more questions?
Yeah.
Mm-hmm.
Just to clarify, technically you have to do the same with decreasing in lower bound.
No, okay, it's not that technically I have to do the same for decreasing in lower bounds. It's that WLOG that we wrote there encompasses both cases by declaring that they're completely analogous and any intelligent reader can see and modify it on his own. And it would be insulting intelligence to write it twice. That's really the statement. Okay? So if you would try to submit a paper for publication in a journal, writing a statement like this twice, the editor would say, no. Cross one of them out and write without loss of generality. You're insulting our readers. Okay? And what I said is be careful. It's not that every time you have separate cases to handle, they're all analogous. Sometimes you need to really handle and you need different arguments for the different cases. Okay? But in this example, you don't. They're really completely analogous, so we just write one and leave it to whoever reads it to understand that the other one is exactly the same and does not really need to be rewritten. Okay? Yes? I said that there exists an element in the sequence, a specific element, capital N, bigger than this. Because if all of them were less than or equal to this, that would mean that this is an upper bound. And that cannot be because L is the smallest upper bound and this is smaller than it. Okay. So maybe more questions a bit later. Let me just remark, or let's call it also a theorem. Every monotone sequence. So what did I drop here? I dropped the word bounded. Okay, every monotone sequence either converges. Well, that would be kind of trivial to say or diverges. Either converges or goes to infinity or minus infinity. So it cannot diverge like minus 1, 1, minus 1, 1, minus 1, 1 of just not having a limit. It either, let's just orally argue the argument without writing anything, arguing the idea of the proof. If it's a monotone sequence, we have two cases, and this time it's very different cases. Case one, it's bounded. That's the harder case. But if it's bounded, we proved it. We're done. If it's bounded, it converges. That's the previous theorem. Do you agree? Case two, which is not without loss of generality, it's a different case, is the case where it's monotone but not bounded. Okay? So if it's monotone, and not bounded, suppose it's increasing, monotone, not bounded, what's the limit going to be? It's going to go to infinity. And proving it would be running kind of a similar argument like this, but without the notion of the supremum, just with infinity, and using the definition of limit of an equals infinity. Okay? It's not harder than this. You can try it. And then you can assume that it's monotone decreasing, in which case it would go to minus infinity. Yes?
Can you give one example for monotone sequence which hasn't got bounded and it converges?
No. A monotone sequence, if it's bounded, it converges to a finite limit. That was the previous theorem.
Yes.
If it's not bounded, it goes to infinity.
And you said either converges or goes to infinity.
Right. And the either says there are two possibilities, and I'm telling you how those possibilities split.
What I'm saying is if it converges, it's also bounded.
No, not from both sides.
So maybe I'm not following your question. If it's bounded, then it converges to a finite limit. That was the previous theorem.
And can't we say also that if a sequence converges, it's bounded?
The fact that if a sequence converges, then it's bounded, that's a much more elementary fact. I think that was like our first theorem when we mentioned limits of sequences. That if a sequence converges, then it is bounded. We proved it.
Then it's bounded from one side, but not from both sides.
If it converges, it's bounded from both sides.
What about one
If it converges, then from a certain n onwards, all the elements are going to be in L minus epsilon, L plus epsilon. Right? We proved it. 1 over n is bounded. It's bounded from above by 1 and from below by 0. Sequences. Don't confuse with functions. Okay? Okay, so that's this statement. Okay, so there's in fact there's a dichotomy here. Whenever handling monotone sequences, that's a powerful thing to be monotone. If you just encounter a sequence along your way to school, it's probably not going to be monotone. Okay, but if it is, then if it's bounded from above, if it's increasing and bounded, it's going to converge to its supremum. If it's decreasing and bounded, it's going to converge to its infimum. If it's increasing and not bounded, it's going to go to infinity. If it's decreasing and not bounded, it's going to go to minus infinity. Clear? Everybody? Okay. So now I want to go back to this sequence here, the 1 plus 1 over n to the power n that we mentioned. And as I said, proving the statement that I'm going to make now, which we made before, that the limit is e, I'm not going to prove it. It just takes some work that I'd rather not spend time on. But the claim is the following. So example, an equals 1 plus 1 over n to the power n is monotone increasing. That requires proof. We're not proving it. And bounded between, let's write bounded an is greater than or equal to 2 and less than or equal to 3 for every n. This requires proof as well, and this is not easy as well. Maybe the greater than or equal to 2 is easier, but showing that it's less than or equal to 3 takes some work, and that's the important thing. So when you're handling a monotone increasing sequence, what's important is to show that it's bounded from above, right? That's what you're seeking, the supremum. And both these facts require proof, and we're skipping them. You can find them in books, or if you want, you can come to me and I'll show you the proofs, or you can think about them. But that's a bit unfair to give somebody to try to invent these proofs on his own. But the conclusion is, by the previous theorem, hence 1 plus 1 over n to the power n has a limit. A finite limit. And that limit, what do we know about it at this point, having stated these facts? That it's something between 2 and 3. That's all we can say, right? It's some number between 2 and 3. Okay? The limit, which is between 2 and 3, is called, just a name, E. Some people claim that E stands for Euler, which was Euler is spelled E-U-L-E-R, and some people claim that it stands for Euler, who explored this and studied this. Okay, and we're going to use this E a lot. It's a number that kind of naturally shows up in places, in unexpected places. It's kind of a number from nature, kind of like pi. Okay, so not every number just shows up when you look at circles or when you look at stuff, and this one is one of them, and we're going to use it a lot. And the only facts maybe that I want to say about it is that E is known to be irrational, so it does not belong to Q. I think even Euler knew that already. And E equals, so we will see later on in the course methods for how we know what E really equals. That we will see. Okay, but for now it's just a fact from the future, if you want. So it equals 2.7182 ... Yes, it will be one way to find these digits more precisely would be to use Taylor polynomials. We'll see that. We'll see that. We're not there yet. Yes, questions? Hmm?
Why you state that it's smaller or equal than 3 and not like smaller or equal than 2.8?
Well, it is. It's smaller than 2.8 as well, but the standard proofs show these two facts, that it's increasing and that it's bounded between 2 and 3. Once you know these two facts, and that's not saying a lot if you think about it, right? It's saying statements that are not limit statements. The fact that a sequence is increasing is not a limit statement. Okay, we did in examples, right? It's something you check for every n. It's not doesn't have the limit phenomenon in it. It's just a kind of a local for any n statement, right? Same for bounded. It's not a limit phenomenon. It's not a limit thing. Okay, and that theorem that we just proved tells us that if you know this and you know this, suddenly you know that it has a limit. Okay? And intuitively we argued why it makes sense. Okay? And then we give the limit a name, E, and we'll see how we use it a lot. You've probably seen already. Okay? Okay. So let me just mention two facts. So this E guy was the limit of 1 plus 1 over n to the power n. Let's call it theorem. So part 1 will be that in fact, if you take the limit as n goes to infinity of 1 plus, and instead of 1, put anything here, put x. over n to the power n. So x here is now a variable. This is not a function. This is a sequence, and x is fixed. Put any x you want there. Okay?
It's a constant.
Right. For this thing, it's a constant. If x confuses you, call it a. Okay, good. Put any a you want there. The limit is going to be e to the power a. Okay? When it's 1, it's e to the power 1, and it's e. So that's one statement, which is very useful. Another statement is that if an is not 0 for every n, and the limit of an is infinity, this is kind of redundant because if the limit is infinity, then it's not going to be 0 from a certain n onwards, right? Do you agree? That this is not really necessary, but let's leave it in there. Then the limit as n goes to infinity of 1 plus 1 over an to the power an is also e. So you can put here, and here, as long as you put the same thing in both places, any sequence that goes to infinity. In the original example, you just put the sequence n. But you can put here, in fact, any sequence that goes to infinity, and that limit is still going to be e. Okay, I'm not proving these. Maybe we'll take a break, and then we'll do one or two examples. So let's take a break now.